Hey folks, this is the second part of our climate lecture that we are continuing on from earlier this week. We're going to talk about ocean acidification next, and I don't want you to worry about the chemistry behind this. What I want you to know is that carbon dioxide dissolves from the atmosphere into the oceans. We know that there's dissolved gases in the ocean, things like oxygen and carbon dioxide, because that's what fish and plants down there are using to photosynthesize and respire. When we put more carbon dioxide into our atmosphere, it means that we have more carbon dioxide dissolved into our ocean. When that happens, it drives a reaction that puts this bicarbonate into the oceans. And this is a slight acid. This is a weak acid. But if we build up enough of it, then we end up with pH changing in the oceans. And pH is our measure of acidity or basicness, or alkalinity. We know the acidity of our oceans pretty well back to 1900. And what we can tell from acidity over time is that our oceans are becoming more acidic. So this is back in 1900. We have measures that are someplace between 8.15 and 8.2. So these are different locations of the ocean. And so these are slightly basic levels. So a neutral pH is 7. Anything below that is acidic. Anything above that is basic. So we have slightly basic salt water, a slightly basic ocean water back then. If we look at our change over time, however, we see a slight decrease until we get to, gosh, around the year 2000. And now we see a pretty accelerated drop in our pH, suggesting that we have increasing acidity. Now, if we look at this over time, if we look at a prediction of what's going to happen in the future, we have two different predictions. We have sort of a worst case scenario, which is meaning if we don't do anything to change the amount of carbon that's going into our atmospheres, we could end up with a big change in acidity. Or if we do something, if we tackle climate change, we might see a steadying of our pH. Now, why do we care about this? The things that live in the ocean rely on a pH that is slightly basic because when it becomes acidic, it is hard for them to build their shells. So let's look at this. This is a snail, a larval snail that is just forming its shell. And if we put this shell into acidic solutions, we can see what happens to it. So it starts to crack here. See how it's getting sort of opaque? It starts to dissolve, and eventually this is what the shell looks like. So things like snails or oysters, anything that needs to build a shell, has trouble building it, or if it's already built it, has trouble maintaining it. This is true for really small things too. We've seen our coccolithophores before. Remember, those are the algae that grow shells, right? And if we put them into water that has more carbon dioxide that is dissolved into it, we see some changes in what their shells look like. So this is less carbon dioxide and lower temperature. This is more carbon dioxide and higher temperature, and you can see this guy here is just a hot mess, right? So he's not very well protected. And not only is he not well protected, he also might have trouble staying afloat. Remember, one of the things about phytoplankton is that they need to stay up near the surface. So one of the things we're finding is that when they have trouble building their shells, they actually sink, and then they get out of the photic zone and they can't photosynthesize and they die. Another example of a species that can't handle acidification would be corals. So this is our little coral polyp, and this is the skeleton that he lives in. And the way that he grows that skeleton is he grows it in sort of a series of layers. So these are all old layers, right? And he builds this sort of, I don't know, brick wall kind of thing here, right? And then he fills this in. He fills it, it's called lateral thickening. And then he keeps building that up, and that's how corals grow. What we know is that when corals are in are in water that is too acidic, they can no longer grow these walls anymore, and so they no longer can have this nice skeleton that they live in. So there's lots of species that can't handle acidification. So as we see an ocean that is acidifying more and more, we may see less and less shellfish, less and less corals, less and less things like coccolithophores. So this can really affect a broad suite of species. So let's talk about sea level rise. We've talked about this a little bit, but let's get into this a little more in depth. So let's see here. This graph shows us sea level rise over time. And so this 0, this is the level of global average sea level in 1880. And then this is in inches, all right? And so what we see is that we have a rising trend in sea level, okay? And that if we get to around now, we have, if we just come right over here, we have about 10 inches on average around our globe of sea level change since 1880. We have three drivers of sea level rise. One would be melting ice sheets like we see in Greenland. We have another one on Antarctica. We have melting glaciers, which behave very similarly to ice sheets. But then we also have ocean thermal expansion. So warm water expands. It takes up more space than cold water. So if we warm the oceans, they take up more space, and the space that they take up, they need to go up. All right. So these are the things that cause sea level rise. Let's look at what happens here in Georgia with sea level rise. So this is what we call blue sky flooding or nuisance flooding, or you can even call it king tide flooding. And it's flooding that's occurring not because of a storm like a hurricane, but simply because sea level is rising. In some places, this can be a real problem because our infrastructure was not designed for sea level rise. So this is Highway 80 going out to Tybee Island. You can see that we have flooding in the marsh and flooding in the canal there. But look, it's up and over the highway, and they're actually having to rebuild that highway because of this blue sky flooding. It floods so often. This is the tidal gauge out at Fort Pulaski. Fort Pulaski is like right around here, and we can see that we have sea level rise occurring there. We have around a foot of sea level rise at Fort Pulaski over the last 100 years. So we are seeing sea level rising right here in Georgia. What does this mean for Georgia? Well, let's look at the predictions of what we can expect. These are from the United States NOAA. This is the National Oceanographic and Atmospheric Administration. These are people who help the Weather Channel and the local weatherman to predict the weather. They're interested in the oceans and the atmosphere, and this is what they are predicting will occur in the United States. So we have several scenarios. If climate change isn't bad, if we do a good job of tackling climate change, then we can expect to see 7 more inches of climate change over the next 50 years or so. If we're bad at it, though, we could see that climate rises by 6.5 feet. All right. So would that mean to Tybee Island? So this is a map of elevation on Tybee Island. And let's see here. 0 means that it is sea level. And then let's see. Anything that is green or slightly greeny yellow would be, under this scenario, inundated. So all of this marsh can be expected to be inundated. Um, all along in here can be inundated. All in here can be inundated, right? Sort of the outskirts of town here, we can expect to see inundated. So, in here, we can expect to see inundated. So for Tybee Island, you can imagine that a lot of Tybee, they're expecting a lot of Tybee to flood on a regular basis and probably become unlivable. So what does that mean to Georgia? And this doesn't occur just on Tybee Island. It's that Tybee has done a good job of actually preparing for this and studying it and figuring out what's going to happen. St. Simons will be in the same boat. Jekyll Island will be in the same boat. Lots of Brunswick will be in the same boat as well. So what does this mean? So one of the things that we know it means is that it will become very hard to live on these islands, and that has had an effect on real estate. Interestingly, for years and years and years, waterfront property was the thing to own, and the price of waterfront property rose at a higher a faster pace than the rest of real estate. But that is not necessarily true anymore because people are having second thoughts. Do I want to have that waterfront home that's probably going to flood in 20 or 30 years? Um, it's such an investment that most people don't want to take that chance. So we actually are seeing uh, property values going down all along the southeast coast. So this is a graphic that suggests that 600,000 properties lost value along the coastline, and about 11,000 of them were in Georgia. And this suggests that waterfront homes in Georgia are actually losing value because of climate change. And you can see, ooh, look in Florida, like 400,000 of them are losing value. And then just really briefly, I want to mention that don't just think that sea level rise is going to affect people living right on the water, because one of the things that happens with sea level rise is that we have trouble with saltwater intrusion into our wells. So if you live near the coast, this is something to consider. So saltwater is denser than fresh water. So when we have a meeting of the ocean and land, this saltwater actually goes under the land into the water table, but because it's dense, it stays low. But if we have sea level rise, we can have that salt water intrude into the freshwater reserves that we have, okay? And when that happens, our wells become saltier, and we do see this all around the coast. All right, now this was not the most cheerful of all lectures, but it is a very, very important lecture. Climate change is the most important thing for you and I to think about. And even though we get distracted by a lot of other things, it is very, very important. It not only threatens things like polar bears or things like real estate, it threatens us. It threatens our health. It threatens our future. It threatens things like our cultural stability, our agricultural stability, even our political stability. So I just want to talk really briefly about, what can you do if you are concerned about this? Well, you can do two things. One thing is you can change your own behavior. Things like fly less, drive less, eat less meat. Um, be energy efficient in how you use things. For example, have energy efficient bulbs or use your car less, things like that. Those will all make a difference. Your influence can make a difference. The second thing that you can do is you can work for systemic change, because we really can't change our use of carbon unless we change as a society. So being politically engaged and making your voice heard can really make a difference, right? So those are the two things that if you're thinking about this as you go forward in your life that you want to do, change your own behavior and work towards systemic change. All right. All right. So let's finish up our lecture today by talking about what's going to be on your test. Let's do a real quick review of what you need to know for your exam. The first topic we talked about this semester was marine ecology, and we talked about the idea that ecology looks at the links between living and non-living organisms, all right? And we looked at this in the context of different types of lifestyles of organisms: plankton, nekton, and benthic organisms. So you should know what all of these are. Um, we talked about examples of how non-living components affect organisms, and we gave examples of how temperature affects organisms, how salinity affects organisms, and how hydrostatic pressure affects organisms. So if I gave the example of, for example, the Rocky Intertidal and how temperature affects organisms there, you should know a little bit about that. We also looked at how organisms in each one of these lifestyles have adaptations that help them cope with the conditions in the ecosystem that they live in. So how plankton have adaptations to keep them afloat because they need to be up near the top in the photic zone. So things like they have a large surface area to volume ratio. They have a lot of pores, so that increases their surface area. They have things like spikes that help them stay afloat. We talked about the idea that the nekton have different adaptations depending on how they want to swim. So some organisms, some of the nekton are really, really good at swimming because they've reduced drag. So like this guy here is very, very hydrodynamic. He's reduced his drag. But this lionfish, on the other hand, he has decided to go in a completely different direction. So evolution has taken him in a different direction. And this organism instead has lots of drag, but instead has poisonous spikes. So a totally different way of making a living. So different adaptations. We looked at adaptations in the benthos, and the idea that we have zonation in the rocky intertidal, where things down here near the bottom are really good competitors. They outcompete other organisms, but things up here are good at handling desiccation and heat stress. And we also looked at the idea that we have zonation across a broad array of intertidal habitats. And one of those ideas that we looked at was zonation of in-fauna, things that live in sand and mud, and we gave some examples of things that live in sand and mud, such as this razor clam here, how he's really, really good at digging. Our next topic was biological productivity. This is the idea that carbon is fixed by primary producers using photosynthesis, and that energy is transferred between levels of the food chain. These are the only chemical reactions that you need to know for the exam. So you should know that photosynthesis takes carbon dioxide and water. It uses energy from the sun, and it produces sugar. So this is sugar, and it produces oxygen. And respiration is exactly the opposite. It takes sugar and oxygen, it produces carbon dioxide, water, and it releases energy. So you should know these two chemical reactions. We talked about food chains versus food webs versus energy pyramids, so you should be able to generally interpret those. And we talked about the idea that energy flows through the ecosystem. It comes in through sunlight, but eventually all energy is lost to heat loss, so some of it's lost at all of these levels, right? But nutrients are cycled because we have decomposers. We have the decomposers that cycle energy through the ecosystem. They're reused over and over and over. And we looked at different methods of feeding, filter feeding and grazing, and we looked at many others, so you should review those. We talked about decomposers here. Here's an example of where we have bacteria living down in this black soil because this is anoxic. So we have different types of decomposers in different places. We also talked about deep sea chemosynthesis near rift communities. So these are these worms that have a chemosynthetic bacteria living inside of them. So you should know a little bit about these crazy chemosynthetic worms. One of the important ideas of biological productivity is that if you are a primary producer, you need to have more photosynthesis than you have respiration. Otherwise you die, right? So if you have more photosynthesis than respiration, then you can grow and reproduce. And the area of the oceans where you end up with more photosynthesis than respiration is in that photic zone, up at the top of the oceans. So this is the rate of photosynthesis. You can see that it drops off with depth and eventually falls to nothing. This is respiration. Respiration is a straight line. It's the same. Respiration is the same up here as it is down at the bottom. So this level, this point right here, where respiration and photosynthesis cross one another, this is the compensation depth, and this is the depth you don't want to fall below, because if you fall below here, then you're basically taking more money out of your bank account than you're putting into it, or you're using more energy than you are producing. So this is a really, really basic fundamental concept in marine ecology. So you should know what compensation depth is. Um, we also talked about the idea that we have nutrients that are important and that some nutrients are more important than others. Phosphorus, nitrogen, and silicon are the ones that are really important to organisms in the ocean. We looked at differences in biological productivity depending on where you are. So upwelling and turbulence act sort of like the spatula that mixes up the brownies. If you just put all the ingredients for brownies in a pan and put them in an oven and you don't mix it, you're not going to have brownies, right? So that's the case in the ocean too. We need to have mixing of nutrients up to the surface where the sun is to end up with biological productivity. So we talked about the idea that upwelling and turbulence are the important forces here. The different types of upwelling, we have coastal upwelling and equatorial upwelling. And these two things, upwelling and turbulence, happen a lot near the coastline. All right, so the coasts tend to be very, very productive. We looked at seasonal variation in productivity in different parts of the ocean. So we have, these are the tropics, where it's very low but steady productivity. We looked at, this is the temperate zone, where low productivity in the winter, and then high in the beginning of summer, it falls off. Then we have a little spike in fall as well, because we have a little bit of fall mixing from storms. And then finally, this is the poles. We have low productivity, and then suddenly just one big spike in productivity in late summer. And then finally, we looked at the idea that this productivity travels up the food chain, but there is a lag. So we have, if zooplankton boom like this, the next level of the food chain, small fish, that boom is just a little bit lagging behind it, because small fish take a little bit of time to react to having all of that food. Their numbers go up. As their numbers go up, they're actually eating down these zooplankton. We looked at global variation in productivity. We tend to see low productivity in the middle of the open oceans. We see the highest productivity in the estuaries. Write that down. The highest productivity is in the estuaries. The coasts are also very, very productive. That's an area where we have lots of mixing, so we tend to have lots of productivity in the coasts. We looked at an example of productivity right down here. This is off the coast of Chile. This is typically a very productive area. But then we have this condition called El Nino that occurs every 3 or 4 years. And this is a change in global patterns of weather. When that happens, we don't have upwelling anymore. And so we can compare these two graphs here, where we have, under normal conditions, we have upwelling, so we have cold water at the surface. This is, cold water at the surface. This is temperature. And we have high nitrate at the surface. It may not look high, but it's high. And we have lots and lots of diatoms. And then we compare that to here, where we have the temperatures really, really high because there's no upwelling of cold bottom water. We have, because that temperature is high, we have, and because there's no upwelling, we have low nutrients and we have low diatom numbers. That means there's very little primary productivity. Our next topic was the dynamic shoreline. We talked about longshore drift. You should know what that is. That's the idea that sand moves along with the longshore current. We discussed rip currents. We looked at what lives in the swash zone. And we discussed the difference between summer beaches and winter beaches. This idea that we have summer beaches that have this berm here, and in winter that berm gets eaten away by winter storms. We discussed how dunes work. So dunes move, they migrate. We looked at conditions in the dunes, how it's very, very hot, it's dry, it's salty, and how the substrate moves. So you have to be adapted to handle the movement of what you're growing on. And we looked at dune plant adaptations. Okay, so you should know some dune plant adaptations. We talked about barrier islands, how they're formed. There are basically 3 ways that they can form. Sand ridges can be isolated during rising sea level. Sand spits can be broken during storms, and we can have just growth, vertical growth of a sandbar. We also discussed the idea that barrier islands migrate. They move shoreward. So this is the original place from the barrier island, and this is where it moved to thousands of years later. Our next topic was coastal habitats. We discussed estuaries. Remember, estuaries are the most productive ecosystem. They are very, very high in productivity, but they're very low in diversity. They're a place where fresh and salt water mix, and we talked about different types of estuaries: salt wedges, partially mixed, and well-mixed estuaries. So you should know a little bit about how water mixes, how fresh and salt water mix in estuaries. We looked at some examples of lagoons. These are areas where they're cut off from the rest of the ocean, but they don't have a freshwater input. We looked at the example of the Chesapeake Bay as one of our estuaries. And then we talked about how salt marshes form and how we see plants living in different zones there based on whether it's the high marsh or the low marsh. Three examples of coastal habitats that we talked about were mangroves, seagrass, and coral reefs, so you should know a little bit about all of these. Then we moved out into the ocean habitats. We talked about the neritic zone. This is the zone over the continental shelf, how we have phytoplankton there that occur in patches. And we talked about the idea of ocean fronts where we have different types of water meeting, water of different density, might be warmer or saltier, and that this drives patchiness of phytoplankton in the oceans. Here's an example of what that looks like. We talked about how there are zooplankton in the neritic zone and what some of those zooplankton are. So we have our usual suspects of the copepods, but then we also talked about some other examples. For example, we talked about jellies, and we talked about sea butterflies as well, pteropods. We looked at how fish tend to school and why they do that, what the advantages are, how they do that, and we looked at some examples of how predators can catch schooling fish. So we looked at the example of the dolphins who use the mud plumes, the whales that use the bubble nets, and then how other organisms will do something called bait ball feeding. And then finally, we looked at the organisms on the benthic part of the neritic zone, and the idea that we have this is real sandy here, and this is really muddy here, and so we have different organisms that take advantage of that. Here we have lots of filter feeders, and here we have lots of deposit feeders. We moved offshore from there. We have the open ocean, or the epipelagic part of the ocean, and there we have this other type of phytoplankton called the coccolithophore, and so we tend to have near the coast we have lots of diatoms, and as we move offshore we end up with sort of a more even distribution of diatoms, dinoflagellates, and coccolithophores. We talked about the idea that the open ocean is featureless. That leads to low habitat diversity, and that leads to low species diversity. So most of our species out there all have the same body shape. They all have this fusiform shape, which reduces drag. A lot of them have the counter shading as well, where they're dark on top and light on the bottom. So there's low species diversity there. Less than 2% of the fish species are found there. It's nutrient poor out there. That means we have low productivity out there as well. Some examples of cool ocean habitats we looked at, open ocean habitats we looked at, are the Sargasso Sea. We looked at the deep ocean, and in particular we looked at whale falls. Remember we looked at these weird worms that use chemosynthetic bacteria. So these are Osedax worms, and this is the female, and the males are those little parasitic guys who live inside the female's tube, and she feeds them, and they don't feed directly. Remember, she uses a chemosynthetic bacteria that breaks down the bone. We talked about ocean resources, the idea that we have this exclusive economic zone that goes 200 miles out from shore. Some of the resources we talked about were hydrocarbons, so we talked about how deep sea drilling works. We looked at fisheries, how we catch things, different ways of catching things, different types of nets and hooks and things like that. We talked about the conservation issues that are associated with them and how some of those conservation issues are mitigated. And we also talked about overfishing. We looked at some examples of aquaculture, for example, oysters or blue mussels, kelp, and we also talked about salmon, which is a huge, huge aquaculture operation. All right, so those are the topics that you should know for next week. We, of course, also talked about climate change, so you should know that as well. So your exam will be multiple choice. It'll be open note, open book, open anything, whatever you want to use, all right? But you do need to have it done within the 2 hours of the exam. So spend some time preparing. I wish you all luck. And remember, Friday we will have an opportunity for you guys to ask me questions. All right. Have a good day, everybody. Take care.